This is Dr. Holt. In this video I have a 10 kilogram block. It's on an incline plane. Incline surface has a 40-degree angle coming off the horizontal. I have a static coefficient of friction of 0.25, a kinetic coefficient of friction of 0.20. We want to determine here first whether or not this object is going to accelerate down the ramp or whether the object is in equilibrium. Again, first thing you should always do in these situations is draw yourself a good, complete, free body diagram. Here I have my axis tilted. So first thing I like to do is I like to come down, I label my axes. I'm going to let this be X here, and if it goes this direction, I'm going to allow that to be positive. I'm going to create this as my Y-axis. If it goes up, I'm going to make that direction positive there. First thing to do is to determine the gravitational components that are parallel to the surface and are perpendicular to the surface. If you get confused at all, an easy way to draw that is just to draw your force of gravity coming down. Draw your normal or perpendicular to the surface going this way. Draw your parallel coming back this way here. In this case, if you do that, this will be a right angle here, and this angle here will be whatever this is, 40 degrees. So this coming down will be the force of gravity, and it will equal to mass times gravity. Now to break this into components, this is the opposite to the 40, so this will be mg sine of your angle. We'll call it theta. This here will be mg cosine of the theta angle. Alright, so I will come down here, I'm going to use just these components. I'm going to ignore the force of gravity because I've broken it into two components. The first one I'm going to have coming down will be like this, and this will be the force of gravity in the Y direction. So come here, I'll make that the force of gravity in the Y direction, and again that's going to equal to the mass, 10 kilograms times 9.8 meters per second squared, which is acceleration of gravity near the surface of the Earth, times the cosine of 40 degrees. I'm following just this format here. If you take 9.8 times the cosine of 40 degrees, you will get a value of 75.07 newtons. Now I come down to here. I'm going to draw the one that's parallel. It's coming down. Again, this is mg sine theta, or in this case, it's going to be 10 kilograms times 9.8 meters per second squared times the sine of 40 degrees. I'll straighten it up just a little bit. It's parallel to that. So that value there will be 62.99 newtons here. I draw my normal force going back up, and I draw a component of friction. Friction is going to resist the direction, so we're going to go up this way. Right now I do not know whether or not that's going to be static or kinetic until I determine what my maximum static frictional force is going to be. This is going to be force normal here. I'm going to go back here and make one more change. I'm going to label this. I should have done that. So I'm going to slide this over. Hopefully I can slide it. I can. I'll just move this. I like to label all my vectors. So this is going to be F, G, in the X direction here. There we go. That's a little bit more complete. Alright, at this point, if you want, I'm going to put a mass times acceleration going this way, assuming it accelerates. So my mass is going to be 10 kilograms times acceleration in the X direction. Okay, and you can do this. 10 kilograms in the Y direction. Again, you're making assumptions about what direction you think this object is going to accelerate. We know by looking at this vector that this object's not going to accelerate into the ramp. It's not going to accelerate up, but we can still put that. So now I'm going to label this as just force of friction. We'll change it to kinetic or static once we know. So I go right to the summation of forces. I'm going to sum the forces in the y direction. Even though we can look at this and we know that normal force is 75.07, I highly recommend that you write it out to be consistent. I'm going down here because we set this direction up as positive. I get negative 75.07 newtons plus my normal force is equal to my mass, 10 kilograms, times my acceleration in the y direction. However, as mentioned, we know this object does not accelerate in the y direction, so we set that equal to 0, which means this side will equal to 0. At this point, I will move this over to the other side, and I will solve for my normal force. So my normal force will equal to 75.07 newtons. As I just said it, I highly recommend that you write the component, because it's too often people always assume that normal force is equal to mg cosine theta. That is only the case as there's no other external forces being added to this object. Because if I'm pushing down with another force on this object, then the normal is no longer mg cosine theta. Now at this point I will determine my maximum static friction. And we know in all cases that is going to equal to my normal force times mu of s. So static friction here is going to equal to 75.07 newtons times my coefficient of static friction, which is 0.25. When I do that, I will get a value of 18.768 newtons. I go back to my free body diagram, and you note if I put in the value of 18.768 this way, I have more force going down than I do up. The object's unbalanced. We know immediately this object's got to accelerate because my net force is not 0, so I'm going to have acceleration. So static will disappear because the object's going to slide, and kinetic will kick in. So we'll go back, and now we'll figure out what kinetic is. Now kinetic friction is just going to be normal times mu of k. It does not vary. So I get 75.07 newtons times my coefficient of kinetic friction, which is 0.20. That's going to give me a value of 15.01 newton here. I will go back to my free body diagram, and I will put that value in as equal to 15.01 newton. Alright, at this point I'm going to sum my forces in the x direction and set it equal to mass times acceleration. Summation of forces in the x is equal to mass times acceleration in the x direction. And again, we've determined that if it goes down, we are going to let that be positive. That's going to give me minus 62.99 newtons. Sorry, positive. Caught myself making a mistake. Plus 62.99 newtons minus what is going up. And we said what is going up is going to be 15.01 newton. We're going to set that equal to the mass, 10 kilograms, times the acceleration in the x direction here. I will grab my calculator. I will take 62.99 minus 15.01. That's going to give me a value of 47.98 newtons. That right there, that is my net force, because my net force is the difference between these two forces. I'm going to set that equal to 10 kilograms times the acceleration in the x direction. And when I do that, I get my acceleration in the x direction going down the incline as 4 point, and we'll round, 80 meters per second squared. That's going to be my acceleration with no other forces being applied. Alright, now let's go back and let's look at the picture. We're going to add a force to this. I want to determine right now what force must I push up so this object will not slide down and the object is in equilibrium. So I'm going to add another force here. And I want this object to be in equilibrium. So I'm going to call that a pushing force. I'll do that in black. A pushing force, force P. I'm going to determine what that is. Well, if the object is not in equilibrium, then I'm no longer going to use kinetic friction. I'm going to go back and use static friction. So I will come back to the summation of forces in the x direction. And again, we're going to set this equal to 0 because we're not going to allow the object to accelerate. It's going to be in equilibrium. So I go back, I have 62.99 newtons minus my static friction, and static friction was 18.768, minus F, because that force is going up, pushing force, and we set that equal to 0. When I do that, I get 62.99 minus 18.768. Move this all to the other side, and I will get my pushing force required to keep the object from sliding as 44.22 newtons. All right. Now let's see what else we can do with this. Let's determine what force is required to make this object accelerate up the ramp at 2 meters per second squared. Okay, we're going to create a new pushing force. Actually, let's back up real quick. Let's do one other thing. Let's determine what force P must be to bring the static friction to 0 so the object is in complete equilibrium. Because remember, the static friction values that we applied, that value right here, that's a maximum value. I don't have to go that big. I mean, it can go a lot smaller than that. So if I ignore my friction completely, I could push up 62.99. If I pushed up 62.99 this way, I go back to my free body diagram. If I do away with this and then put on my pushing force, I could ignore my friction, and I would need 62.99 to hold it in place, and I would not even require any frictional force whatsoever. Alright, now what I want to do is I want the object to accelerate up the ramp at 2 meters per second. What's going to take place if I make this object accelerate up the ramp? It's going to move up. Now, kinetic, remember, can switch directions. Kinetic is going to go back the other way now. So I can move it down to here. Kinetic will go back this way. These values will be the same, so I'm just remember, kinetic is resisting motion. Motion is going to move up, so kinetic is going to kick back and go back the other way. So now, to determine what force is required to make it accelerate up the ramp at 2 meters per second, again, we sum the forces in the x direction We're going to set that equal to mass times acceleration in the x direction. Again, we know that it's going to be 10 kilograms, but we're going to make it go up at negative 2 meters per second squared because we determined up was negative. So I'll go back to my free body diagram. I got two forces coming down, 62.99 and 15.01. So I got 62.99 newtons plus 15.01 newton plus, we'll make it minus the pushing force because it's going up and we made that negative. Pushing force is equal to 10 kilograms times minus 2 meters per second squared. I will start adding these together. 62.99 plus 15.01 gives me a value of 78 newtons. So I got 78 newtons minus F of P is equal to minus, that's going to give me a 20. I'm going to move that back over to the other side. And F of P would equal to 98 newtons. So if I pushed up at 98 newtons, all these other two forces would be pushing down the 62.99, the 15.01. That would give me an acceleration of 2 meters per second squared. Again, as I always say, the key to solving all these problems is drawing yourself an accurate, detailed free body diagram, and then off to the side having mass times acceleration. If you don't know the direction acceleration or you can't assume it, just pick a direction and go with it. The math will lead you to the right direction. As always, I wish you the best of luck in physics as you continue to solve more complex problems.